Good day, ISMB. I'm Xixi. I'm a PhD student from University of Tübingen, and I'm going to walk you through my poster about a program that I wrote. The name is Mapbin, and it works on the genome binning problem. That is to cluster a mixture of genomic fragments by their genome arrangements, and is typically used on metagenomic assemblies. Mapbin refines a given binning result, and it's an unsupervised method, so we only analyze the sequence features without using additional biological information. And the motivation is that the conventional genome binners usually use oligonucleotide composition and the contig coverage for clustering. And we want to improve that result using two additional sources of information coming from the assembly graph or the paired end sequencing data. A basic algorithm is very straightforward. It relies on the network data structure for clustering, and it expects three types of user input: the binning result to refine, the assembly graph, and the paired end reads to contig alignment file. So we make each of the three into a network, and the nodes will be representing the contigs. And then we combine all the networks into a multilayer network, which will be passed on to an algorithm called InfoMap for clustering. And based on that result, we can write out the new bins. So how did we turn the input data into networks? For the binning result, basically each bin is made into a connected subgraph, which is disconnected from the others. And the assembly graph is easy because it's already a network. We just need to reformat it so the nodes will be representing the contigs. And for the read pairing, we have to analyze the alignment file, and we expect the two reads from the same pair are supposed to be from the same source genome. And if they are mapped to two different contigs, then we add an edge between the contigs. Of course, these are just the rough ideas. We still need a few steps of fine-tuning, and we did a lot of quality control. This is mainly because we will have a much sparser network in the assembly and read pairing layer compared to the binning layer. So even if we only make a few mistakes in the sparse layers, it will actually affect the clustering output very much. Therefore, we have to remove a few spurious edges, and we also did some preliminary detection and processing of contaminated bins. Sorry for if there's some background noise. I have a thunderstorm here. So next, I'd like to show you Mapbin's performance with a few benchmarking examples. And first, let me explain briefly the setup. Mapbin can be run in three modes, using the assembly graph only, the read pairing only, or both. And we also need to generate the original binning result for it to work with. And for this, I tried different binners. And the Mapbin is in general compared to the original binning result it used. So for different runs on the same dataset, we compare the common bin quality metrics. And there are 6 of them here. Apart from the number of high-quality bins, the rest 5 are all overall statistics for all the bins generated by the tool. And they include completeness, purity, accuracy, F1 score, and the adjusted rand index, the ARI. In this first example, I made a simulated dataset called random. It's short-read assembly used with 3 original binners, Metabet, Concoct, and Maxbin, and 1 additional bin refinement algorithm, GraphBin. So the general impression with this dataset, as well as with the other short-read dataset, is well, Mapbin has achieved, let's say, small-time success in increasing the number of high-quality bins, but it does improve the overall statistics for of the bins. So if your original binning result contains many impure bins like Maxbin here, Mapbin is effective in reducing the contamination. And if your original binning is already quite decent, like Metabet and Concoct here, Mapbin can increase the completeness and the other metrics. The next dataset is taken from the regional market because this is from the second round of Kami Challenge and it is featured in this microbiome COSI. But if this is new to you, Here we have 5 datasets. They are microbiome from 5 human body sites publicly available. Each dataset has around 10 samples, way more complex than the previous simulated dataset. And they all have a gold standard assembly and ground truth for binning. Because I want to work with the gold standard assembly here, so I did not do the assembly myself. And I used only the read pairing mode of Mapbin because I have no assembly graph. And in the high quality bin plot on the left, the blue bars are the originals, and the oranges when they are used with Mapbin. And on the other plots, the letter shades are originals, and the darker ones are Mapbin. So you could notice there is a significant increase for all the 6 metrics and for all the tools. Compared to the previous one, it is breathtakingly better. And this is mainly because the dataset contain a number of long contigs that are close enough to a complete genome on their own. This usually won't happen for short read assemblies, but here they got mixed up in the original binning. And the Mapbin successfully detected the bin contamination and liberated these long contigs from their original bins. So there is a significant improvement. With this, I presented you a tool that does bin refinement called Mapbin, and it works with both short and long read assemblies. I'd like to thank you for listening. And this is my poster, and you can find my source code in this Git repository, and you can find me in Lyon explaining to you more details, and I'm also open to more discussion.